All right, so we're in this chapter on heat exchangers. This is our second and last lecture in heat exchangers, chapter 11. We covered a lot of ground. There's two methods for analysis or analyzing heat exchangers. One is the log mean temperature difference method. That was the preferred method many years ago, but basically the effectiveness NTU method is the method emphasized in this chapter and a lot easier to use in practice. But you want to still know what is the log mean temperature difference and how you can use it for simple, let's say, concentric tube heat exchanger configurations. But when you start to get shell and tube, the older method, the log mean temperature difference method, had a correction factor introduced, but this textbook has taken that out. Earlier versions of the textbook had the correction factor in there and how to handle shell and tube and other configurations, but it's no longer in the textbook. So if you want to do a shell and tube type of heat exchanger, different configuration, cross flow, mixed or unmixed, effectiveness NTU is the method to use. All right. So what was this effectiveness NTU method? We introduced it last time. All it is, it's kind of abstract, is a relationship between these two parameters. And you can do it in equations, and you'll see, oh, here's an equation where if I want to get the effectiveness, it's a function of the number of transfer units and then the ratio of heat capacity rates. Or they'll turn the equation around and they'll have, if you want the number of transfer units, it's some function of the effectiveness and ratio of heat capacity rates. That seems a little abstract. You mean that's the method? Yeah, these correlations. Sometimes they'll put them in a plot. They'll put the NTU as a function of effectiveness for different heat capacity rate ratios, CRs. And so how do you use that? Depending if you're given the NTU and you want to come across and calculate the effectiveness, or if you know what effectiveness you have or need, then you come and calculate the NTU. The number of, so what is exactly the effectiveness? It was the actual Q divided by the maximum theoretical possible. What is the NTUs? The number of transfer units. What's it defined as? UA divided by the minimum heat capacity rate. All right, what is U again? Overall heat transfer coefficient. What is A? Area. What is C? C is our heat capacity. So we have it of the cold fluid. It's the mass flow rate and the specific heat of the cold fluid. Likewise, the heat capacity rate of the hot fluid, which is the mass flow rate, specific heat, constant pressure of the hot fluid. Professor, what happens if one of those fluids is changing phase? Well, if one of those fluids is changing phase, its effective specific heat is as if it's infinity. All right? So you have a very large heat capacity rate. Now, how do you get the minimum of them? You just take the minimum. You have two of them. Which one's larger? Which one's smaller? The smaller one is the minimum. The ratio of heat capacity rate, C sub R, is C min divided by the other C, which would be the maximum C. Now, if they have the same value, it's 1. Otherwise, it's less than 1. Can it be ever greater than, well, it only ranges between 0 and 1. It can't be greater than 1. It can't be less than 0. All right, maximum delta T. This is the temperature hot in, is the highest of the hot temperatures. And then you have the coldest of the cold, that would be the cold in. So those are your two extreme temperatures, so that's our delta T maximum. And if you calculate the maximum rate of heat transfer, right here it's a theoretical, it would be the minimum heat capacity rate multiplied by that temperature hot in minus temperature cold in, the maximum delta T. All right, and then the actual rate of heat transfer, Q, is actual, sometimes I'll put ACT, so it's not to be confused with MAX. But the book doesn't use the additional subscripts, but every now and then I'll add it. And that's just that's just your actual rate of heat transfer. You predict it by basically unraveling the effectiveness in the NTU method, effectiveness NTU method. So once you get Q, then you can go back to energy balance equation. This is really our rate equation for the heat exchanger. The energy balance for the hot fluid, we know Q is the heat capacity rate of the hot. Then we have the temperature hot in minus temperature hot out. You go back to the energy balance equation for the cold fluid. That same rate of heat transfer into the cold fluid is equal to the heat capacity rate of the cold times the temperature cold out minus temperature cold in. That's a review. Last time we covered a lot of this, but you got to start using it before you become more familiar with it. Well, last time we showed a lot of the work that other people have done and tabulated these relationships. So in this table, the textbook, they have, here's an equation where on the left-hand side is effectiveness. So if you're given the NTU and C sub R, you can calculate the effectiveness for a parallel flow concentric tube configuration. Here's a counterflow concentric tube configuration. Here's a shell and tube with one shell pass and N is 2 or 4 tube passes, and you can see that the equations get a little complex. But that's just somebody did a lot of work and tabulated these for us. Here in the 11.4, another table, this is the NTU. So it's as if you're given the effectiveness in C sub R, how to calculate NTU for different configurations. So the effectiveness, if you think about it, it tells you or allows you to calculate the rate of heat transfer. So if you know the effectiveness, you know the rate of heat transfer, what you need to accomplish in the device. If you know the NTU, it's basically the size of the heat exchanger, how big it is. Its area is in there. So this effectiveness gives you basically Q, the size, or NTU gives you the area. So two things in heat exchanger problems. Either you're sizing it or you're rating it. Here are the plots. You can tell here's a plot for this one shell pass, then the tube pass back and forth, or here's 2 shell passes. And again, you could come in here knowing the size, calculate the NTU, come up, whatever ratio of heat capacity rate you're at. Maybe you're at this value. That looks like a value of 0.5. And then read off 0.8 would be the effectiveness. Or if you know what you need to accomplish and you need to figure out what size it is, you come over and then read down to get how the number of transfer units and you're sizing it. So either you're going this way, you're rating it, the heat exchanger, or you're going this way and you're sizing the heat exchanger. Here's that definition. I didn't get through it last time. The definition, or not the definition, the derivation is a little abstract. But the bottom line is, for the effectiveness NTU method, the heart of the method is some correlation where I have NTU related to effectiveness, some equation. And then you use all the other equations to use it. So you can calculate then the area or the rate of heat transfer. So all of this on one page is to get the effectiveness NTU relationship for a concentric tube counterflow heat exchanger. So we define our hot in, hot out, cold in, cold out. What is this equation? It's what we already had out there. It's our log mean temperature difference equation to predict the rate of heat transfer, Q. These are definitions of the large C heat capacity rates for the hot and cold. This is where it seems a little funny, but in the derivation, you just pick one. You just pick, let's say, the hot fluid to be the minimum. Well, what happens if the hot fluid's not the minimum? The cold fluid's the minimum. Actually go back and redo the derivation, picking a different route, and you'll see that it gets the same result. I think it's easiest if you just pick one and continue the analysis. So pick or assume the hot is the minimum. By definition, the Q max is C min times this delta T. The effectiveness is by definition, and so Q is equal to the effectiveness times the minimum, hot minus cold, just expanding. That's like therefore. Now you come over here and you say, well, from the energy balance of the hot fluid, isn't this true? So the hot out is that. Now I can substitute for Q, and I get an equation for the temperature. It's all algebra, but it's like insightful or guided algebra to finally get this equation down here. Okay, you define C sub R, and for this problem, because hot was the minimum, it's hot over cold, and the cold fluid outlet temperature from an energy balance, just like this was the energy balance of the hot fluid, energy balance of the cold fluid. This gives you the equation for T cold out. You see that Q, what do you want to do? Replace it with there, and you get another equation. Doesn't look like it's going very far, does it? I know, kind of get lost in the forest, but we need to know where we're going. We're just getting an algebraic expression between effectiveness and NTU. All right. What am we doing here, delta T1 and delta T2? Well, we're going to come back to this log mean temperature difference. So let's get delta T1. Well, that's hot in minus cold out for a concentric tube counterflow heat exchanger. We already just calculated the cold out, so use that to expand. And you can collapse algebra. Let's do the same thing for the delta T2 on the other side. That's equal to hot out minus cold in. We already expanded for hot out. Let's substitute in. Collapse a little algebra, and there's a packaged expression for delta T2. Put them in the log mean temperature difference, right here. When you put them in and you play with the little algebra, this is in my way, isn't it? Get that out of the way. Some things cancel and algebra rules. There you go. You can get that relationship. So substitute now into this equation for the log mean that you just derived. The Q, so on this side it's UA, then the log mean temperature difference, but Q is the effectiveness right here times the minimum times hot minus cold inlets. Some cancellation of terms. Now you bring the UA and divide by C min. Why did we do that? Because other people have worked on this and they've identified that as the number of transfer units. And so now we see, oh yeah, here's the definition of number of transfer units. And then we see over here it's a function of effectiveness and ratio of heat capacity rates. You're probably like the other undergrad students who I've done this lecture before. You're probably underwhelmed. Like, what? But this is it. It really is insightful when you start to use the method. And a lot of people put a lot of work into it. And the bottom line, I need those relationships. Now, somebody says, take this relationship and flip it around. I want effectiveness as a function of NTU and C sub R. More algebra. It's just more algebra. So this is the equation. Oh, I forgot. I should say that you can manipulate this equation algebraically, compare it with what's in our textbook, and it's the same equation. Sometimes it's packaged a little differently. But now what we can do is take this equation, algebraically manipulate it, and get another expression where its effectiveness is now a function of NTU and C sub R. This is all algebra. It's not even calculus. But it's insightful, like, oh, what do I do here? Oh, I need a minus sign. I cancel this term. I group it this way. And there you go. Okay? Okay. So, step back and say, I want you to solve a counterflow heat exchanger, concentric tube counterflow heat exchanger. These are the inlet hot and cold temperatures, the mass flow rates, the specific heats, the area, the overall heat transfer coefficient, and calculate Q. Calculate the hot outlet, cold outlet, and then the log mean. You don't really need this using the effectiveness NTU method, but it's nice to compare it. So this would be an equation here that is copied, so you would go and say, hey, it looks like I can get the NTUs pretty easy, and then I'm trying to calculate Q. If I'm trying to get Q, I'm trying to rate it, hence I need the effectiveness. So this would be the preferred equation. Okay, well, how do I calculate the number of transfer units? UA over C min. How do I get C min? First I get the C for the cold. Isn't that the mass flow rate of the cold, which is 3 kilograms per second, multiplied by the specific heat of the cold, 1.8. I think that's 5.4 kilowatts per Kelvin. Heat capacity rate of the hot, mass flow rate of the hot, 2 kilograms per second, times 4.2. So that gives us an 8.4 kilowatts per Kelvin. The minimum is the 5.4 for the cold fluid. So now at this point I can calculate the number of transfer units. I know the value of U, 1800. Caution, because here I have watts per meter squared degrees C. The area is 4.3 meters squared, but I'm dividing by C min, and if you look at it, look at the unit on this joule right here. It's not 4,200 joules, it's 4.2 kilojoules, hence we had kilowatts. So either way you handle this, you can put down here the 5400 watts per Kelvin, but don't be off by a factor of 1,000. It comes in about 1.4333. Okay. Does that look good? Somebody run it on the calculator. Thank you very much. So now I have the number of transfer units. I can get C sub R, that's the ratio of min to max, 5.4 divided by 8.4. So it comes in 0.64286. So there you go. For 3 places you need to put in C sub R, 2 places you need to put in NTU, and you can calculate the effectiveness for this problem, 0.6518. If your effectiveness comes in, greater than 1, look for an error. If it comes in negative, look for an error. Okay. And so our maximum rate of heat transfer is our C min, which is 5.4 kilowatts per Kelvin, times temperature hot in, which is 90, minus to temperature hot cold in, 40. And Qmax comes in at 270 kilowatts. Knowing the effectiveness and the maximum rate of heat transfer, you calculate Q is equal to effectiveness Qmax. And you'll calculate 176 kilowatts. All right? How about once you have that Q, it's pretty easy because the temperature hot out from the energy balance of the hot fluid. So we have that Q is equal to the heat capacity rate of the hot, temperature hot in minus temperature hot out. And you just solve for the temperature hot out, knowing Q and everything else, and 69.05. Likewise, energy balance for the cold fluid. The same Q, 176 kilowatts. Heat capacity rate of the cold, temperature cold out minus temperature cold in. Solve for temperature cold out, and you calculate 72.6. Look easy? Good. Ready to press on? So with that, I need to switch right here. Let me jump over here. I have a very long counterflow concentric tube heat exchanger. It has hot water at 120 and that mass flow rate coming in. It has cold water at this temperature, 30 degrees C, and 2 kilograms per second at that mass flow rate. So we read this a couple times over. It's water and water. Both sides are water. Now, one is hot, one is cold, but as a first approximation, the specific heat of the constant pressure of the hot fluid, which is water, and the specific heat of the cold fluid, which is water, is the same. Just assume it's the same. Likewise, the mass flow rates. Is one flowing faster than the other? Hot fluid, cold fluid? They're the same mass flow rate. Okay. Now, they don't come in the same temperature. One is truly hot and one is truly cold. Okay. But it's a counterflow concentric tube heat exchanger. So you can maybe make the configuration, put the hot fluid going this way, cold fluid going that way. Remind yourself, okay, so I have that the temperature hot in, temperature cold out, the temperature hot out, temperature cold in. Okay. But then I look at this description of the size of that heat exchanger. What do you mean very long? What does that say to you that it's that is very long? Like, what about this area? Yeah, it goes off to infinity. And now somebody already has some insight saying, if it's very long, it's like it's infinitely long. You know, there's the illustration where there's a break and blah, blah, blah. And so if you said, what is the hot fluid outlet temperature? You can input that now or make that calculation. Some of it just from insight into the problem. I heard some students saying it verbally. Or through the equations and the analysis methods that we just demonstrated. So let me do this. Let me switch this over to numeric response and ask you to input your calculation of the hot fluid outlet temperature in degrees C. So maybe what you do is you go through a thought process and you're going to plot as a function of location X from 0 to L for a finite length heat exchanger. And you're going to come in here on the y-axis and plot temperature, and you're going to put a numeric value of, let's say, 120. Try and draw it to scale. You're going to put another value of 30 degrees, and there's the 30. Actually, the 30 is coming in on this side, and I drew it where the hot is on this side. And what it would be is the hot would, as it flows that way, cool down, and the cold would heat up. But if I increase L and do it again, and increase L and do it again, you know, just make another plot, and here's L now. And I try to draw it to scale, to 120 and to 30. And there's my blue, and there's my red over here. What you find is that the delta T gets smaller and smaller and smaller, doesn't it? As you get larger and larger and larger. And so from some insight into analysis of heat exchangers, we would have that the temperature of the hot fluid going out, that would be right down here, would be the temperature of the cold fluid going in for an infinitely long heat exchanger, very long heat exchanger, infinite area. And so it would come at basically 30 degrees. Does that make sense? All right. Somebody says, how do we use our equations that we just learned and solve the same problem? Okay. So we go and we say it's a counterflow, concentric tube. And let's take a look here. We had the same hot and cold fluid mass flow rate, specific heat, hence the ratio of heat capacity rates is 1. C sub r is 1. So this would be our fun equation. Now, you say the number of transfer units is UA divided by the minimum heat capacity rate. For a very large or very long heat exchanger, What is A? Very large. What is NTU? Very large. So now if the NTU goes off to infinity, very large, or even just put in 1,000 or 10,000 or 20,000, 100,000, million for the NTU, and you'll see that, by adding 1 down here, it's negligible. So what does the effectiveness do? It goes to 1. Okay, so now if I know the effectiveness goes to 1, then what is the Q actual? It's equal to Q max, which is the minimum heat capacity rate times the temperature hot in minus temperature cold in. But the heat capacity rate's the same whether it's hot fluid or cold fluid. That's the same as saying C sub R is 1. So I need to move this out of the way, maybe scoot down a little bit. So this is from my rate equation, how it's controlled by the area, the overall heat transfer coefficient. My energy balance equation for the hot fluid is Q is equal to heat capacity rate of the hot, temperature hot in minus temperature hot out. These are the same. So Q is equal to Q. The C sub R is, I don't know if I need to go slower or faster, but you get the equation that Q is equal to Q, that C min T hot in minus T cold in is equal to C hot, T hot in minus T hot out. These cancel, this cancels. The hot out is the cold in. You prove it mathematically. Well, that was a simple case, Professor. I know, we're getting warmed up. Okay, so let's, this is actually the calculations. Oh no, sorry, I got to back up. This case was our case that we just solved, the counterflow. Guess what you do now? Oh, we're tired, we're bored with counterflow. Let's do parallel flow. Okay, here's the thing for the parallel flow. I'm supposed to not let you see the solution, so I need to sort of rub it out. Sorry. You already saw it? Oh, you didn't see it. Okay. You can't read my slide? I can't read. You can't read? I did one. It's been at least 10 years ago. A student came up to me and he said, we're talking, and he said, I graduated with the complete Bachelor of Science in Mechanical Engineering degree, and I didn't read one book one time. And I thought that's pretty sad, because I'm not certain that student's going to be well equipped out there in the world. Because when I did senior design and I would tell the students on this one team, read the instructions and get the specifications and read the manual, because I don't think this equipment's installed correctly. And they were working with a company and they're like, oh, we looked at it, it's installed. It's not installed correctly. There's something wrong here. Oh, no, we read it, blah, blah, blah. They didn't read it. I finally give it to me. Sit down with them, open it up. What's that say right here? Oh. And I've found, because every now and then I do some consulting work with attorneys, that when crap hits the fan and the engineer's to blame, it's often because they didn't take a look at some of the details and some of the equipment. And they put the equipment in when the details say, don't install it this way, don't run it this way, only do it this way, feed it this type of fluid, don't let the temperature do this. And, you can get yourself in a big trouble by not being able to read, and especially technical stuff. It's dense and hard to read, so please learn to read. I know you're joking with me, but that one student wasn't joking with me a couple years ago. It's like, Professor, just give me your PowerPoint slides. I don't want a book. I won't even come to lecture. I won't even bother you. I'll never come to your office. Just give me your PowerPoint slides, and then we're happy. I'll kind of glance at those. Anyway, I got off on a sidetrack. Let's solve this problem. So we have now parallel flow. What does that mean? Everything's the same. It's very long. The same inlet temperature, the same outlet I'm sorry, the two inlet temperature the same, the two mass flow rates the same, and still water. I would make a good sketch of this and say, okay, what direction is the hot fluid flowing? What direction is the cold fluid flowing? Maybe make a sketch of the temperature from 0 to L. And the hot comes in 120, the cold comes in 30. What do you think the temperatures do? They're going to do something like this, especially if it's really, really long. If it's really, really long, long, what is the difference between those two temperatures at the exit? Isn't the temperature of the hot out equal to the temperature of the cold in at the exit if it's very long? Sure. And now you just have to solve for it. So let me do this. I'm going to ask another one. What is the hot fluid outlet temperature in this case? And for the vast majority of you, congratulations. So very good. 75. How did you do that? You're a genius. Well, let me do this. Can we use the equations and the method we just learned to do the same thing? Okay, so if I look down here, I say concentric tube parallel flow, I can find this relationship for the effectiveness, a function of NTU and C sub R, the ratio of heat capacity rates. Can you tell me what is effectiveness for this problem? Another numeric response. What is the effectiveness for this problem? And let's go ahead and show our results. And congratulations, it is a half. It is a half. Yeah. And so basically, this exponential of something, that all goes away to 0. So I have 1 minus 0. But then what is C sub R? It's 1. So I have 1 plus 1, that's 2. So I have 1 over 2 half. Learn something every day. There you go. All right. Now, how do I use that to actually numerically calculate that hot fluid outlet temperature? Well, here I have a quick summary. The actual is the effectiveness times the maximum, that equation. Yeah. What's the maximum? The minimum heat capacity rate times temperature hot minus temperature cold in. Then we had the half for the effectiveness. The minimum is equal to CH or C cold, either one, they have the same heat capacity rates. And then you just equate what is the actual to what happens with the hot fluid. And so the hot fluid's heat capacity rates cancel. And then I have this equation, I just have algebra, temperature hot out, temperature hot in, minus a half of that, which is 120, there should be equal sign, minus a half times 120 minus 30, which gives us what we anticipated. That's all easy. Now, let's say somebody wants to make it a little harder. What do you think they're going to do to maybe this mass flow rate? Up or down? They're going to change the mass flow rates. And then they're going to go back. Hey, concentric, change the mass flow rate. Go back to parallel, change the mass flow rate. There, your intuition may not be as so insightful. Some of you probably can get it. But you would need to rely on the method to make the calculation. So, okay, I'm not, in the interest of time, this is just talk through the solution. Let's say you double the hot fluid flow rate. Double the hot. The cold is doubled. Double the cold, isn't it? 4 kilograms per second, hence it's twice the hot fluid. That's what I'm trying to say. It's now 2 times the hot fluid. Okay, so you basically, if you wanted to, let me draw it up here. The temperature is a function of 0 to L. We're doing the counterflow. So let's put in hot way up here at 120. The cold over here at 30. And the cold is now faster, going through the system at a greater rate. So what happens is the slopes are not the same. The hot may do something like that, and the cold has less of a slope because it's faster going through, and the m dot's higher. Hence, the change in temperature of the cold fluid from inlet to outlet is not as great as the change in temperature of the hot fluid from inlet to outlet. Make sense? Actually, the temperature change in the cold fluid should be half of the temperature change of the hot fluid from energy balance perspective. Anyway, you can follow through the math. Let me scoot down just a little bit here. So we had counterflow. We don't have this. This is not true anymore, is it? We have the ratio minimum to maximum. Because you doubled the flow rate, this becomes a half. And when it's a half, I have to use this equation. I have to put a half there, half there, half there. This is still very large, very large. So I have 1 minus the exponential, something very large, that goes to 0. Then 1 minus a half times, E, yeah. And then how about this one? I'll have e to the very large. That's 0. So what does effectiveness turn out to be for this case? Turns out to be 1. Where do I say that up here in my solution? Right here. Effectiveness is 1. All right. But when you come and calculate the Q max, you have to use the minimum heat capacity rate, which is for the hot fluid. The cold fluid's mass flow rate was doubled. All right. You then calculate that the temperature hot out, when it goes infinitely long, goes to 30. Actually, and then the temperature cold out, it doesn't go all the way to 120. That would be the same slope. It has, this change here was what? 120 minus 30, 90 degree C change in temperature. This one's going to be a 45 degree C change in temperature. So 30 plus the 45, it comes out at 75. 75. Same equations. All right. Well, once you have fun with that, guess what you do? You crank it up again. You go 8 times. And maybe you make it parallel. You can solve these. What I want to do now is I want to just highlight this table in the textbook. 11.2. What do they do? It's the overall heat transfer coefficient. These are representative values. So if I have water to water, you're probably in this range of overall U. If you're significantly out of that range, look at some of your calculations and look at some of your assumptions. Maybe something's off. These are very helpful. And when I talk to students doing a senior design project, often I'll go to something like this in our fluids book or heat transfer book because they got some calculations that's way off. You know, it's like, hey, I made the calculation. I have water-to-water heat transfer, and I have U that's 10 to the 6. Really? Well, I mean, it should be around 2,000 or lower, unless you have some really exotic behavior. So anyway, this helps you. I think this table is helpful. Let's continue on. I want to solve this problem. We have a heat recovery device involves transferring energy from a hot flue gas passing through the annular region to pressurized water flowing through the inner tube of the annulus. So this is the direction of the water flow, and this is the gas passages. The gas passages are made up of the annulus, but then they have this ribs or struts that support the tubing. And those struts are all the way down. They're just solid. And there you go. So the hot gases, let's take a look. They give us dimensions. The inner tube has an inner and outer diameters of 24 and 30 millimeter. So this one is 24 millimeter. This is 30 millimeter. And the insulated outer tube is 75 millimeter. 75 millimeter. And this is all insulated. They're showing it with this notation or illustration. And so each strut has a thickness of 3 millimeter and is integrally fabricated with the inner tube from carbon steel. So this is the thermal conductivity. So all of this material and the struts are the same material, solid, with a thermal conductivity of 50 watts per meter Kelvin. Okay, consider conditions in which the water is 300 Kelvin with a mass flow rate of 0.161 kilograms per second. So the m dot's given. And the flue gas is 800 Kelvin. And through the annulus, maintaining a convection coefficient on the gas side of 100 watts per meter squared Kelvin on both the struts and the outer surface of the tube. So you have convection on the outer surface of the tube that's not covered up by the strut, and then on the surface of the struts, and that's two sides of the strut. Okay. Use the Dietz-Boelter equation to obtain the water side convection coefficient. So they want H on the water side. And then what is the rate of heat transfer per unit length of the tube from the gas to the water? So what is the Q divided by L, where this is 300 and that's 800. I know that as it goes down the tube, the length of the tube, the water is going to heat up and the gas is going to cool, but just at that condition where it's 300 and 800, what is Q per unit length of the tube? So how do we calculate the first part? Dietz-Boelter, right? And so that's pretty easy. So I'm going to skip that calculation because I'm sure you can do it, and that was covered in the previous chapter with internal flow. Now the next part is how do I calculate this Q per unit length? Go slow and make some assumptions. Let's go to another slide here where I can have some working room. I would build a resistive network. I would say I have the temperature of the water. I have the temperature at the inside one, that's like trying to use this notation, inside one. And how does it go from the water, the mean temperature of the water being, what was it, 300 Kelvin, to an unknown wall temperature, the inside surface? Well, it's a 1 over HA. It's a convection. Okay, that 1 over HA would be for the inside one, inside one. Okay, now what do I do? Well, I'm going to have a resistance due to going between D inner 1 and D inner 2. Does that make sense? So I'm going to do a resistance due to conduction from here to here. Now there's an assumption about this, that I'm going to say that the temperature everywhere here is the same. It's uniform temperature. And another big assumption is everywhere here it's the same at the diameter di2. Now, somebody says, I disagree with that. I'm going to propose a different method for the analysis. What would you propose if you were going to say, I think that the temperature is not the same everywhere, at where I have this blue line? Where would it be different? Where the strut covers it up. Now, I'm going to I could come back to that different method of analysis where you would say, oh no, I think the surface right under the strut is different temperature than out here, where it's not covered up. We can come back and revisit that. But for right now, we know that that's an assumption. It's the same temperature everywhere at the same diameter, Di2. Okay. So somebody says, what's my model for the conductive resistance through that? Well, you would say, oh, the natural log Di2 divided by Di1 divided by 2 pi KL. Where did that equation come from? Pardon? That's conduction through a layer in a cylindrical configuration. Often we think about insulation around a pipe. And so that's out of, I forget, chapter 2, maybe chapter 3. Okay. So now I finally have it out to this temperature, which is the temperature I2. How do I get from I2 to the gas temperature? Well, at this point, I gotta do two paths. This is the gas temperature, just like this was the water temperature. This is my, what was it, 900 Kelvin? I can't remember. And this is 300 Kelvin, right? How can it go, the heat from Di2 into the gas? This would be due to the uncovered surface, and this would be due to through the struts. And then first it's strut, and then it's convected. Here it's convected, I'm trying to write this out, convected off of the exposed surface. What do you mean exposed surface? Well, let's try and zoom in a little bit. This part right here, and that part, and that part, and that part are all exposed, aren't they? That's probably the easiest one. So let's do this. What's my model for the convection directly off of the exposed part for getting not covered up by the strut? Wouldn't that be my 1 over the H on the gas side times that area? But the area is a little tricky. That area would be pi Di2L. That's a pretty good approximation, but that's not accounting for the little bit that's covered up by the struts. How many struts do I have? Count them. 1, 2, 3, 4, 5, 6, 7, 8. And how much real estate do they cover up? 3 millimeters. So we have to subtract off. Let's get rid of this thing, put it over here. So we have to subtract off 8 times our thickness times our length. Isn't that right? Okay, you can do that, and then you get this area. Maybe I put it area exposed, E-exposed, some whatever notation you like. Okay, now what about the struts? How am I going to calculate this resistance to go out the struts? Just like this forced you to recall something out of a previous chapter, how do the struts behave? They behave like a fin, right? Basically, it's a fin calculation. So you have to remember, it's like, I have the conduction down and then convective off the fin. It's not a pin fin, it's a rectangular fin, each of those. And I'll have 8 of them. Let's do one at a time. So what's my model for the equation for the heat transfer through a fin? What was my equation for heat transfer from a fin? I'm going to pause, walk around. I want you to write it down. I want you to maybe open up your book. We'll recall from memory. What is that equation for the heat transfer from one single fin? Remember this equation, the hyperbolic tangent of ml divided by ml, where m is that fin parameter and l is the length. It's for insulated tip. Hey, what was that equal to? That's equal to fin efficiency. How do we use that fin efficiency? Yeah, this is equation 3.95 in my version of the textbook. Right. Okay. How do we use that fin efficiency? The fin efficiency times Q fin maximum, the absolute maximum from a fin surface. What is the equation for the maximum off of a fin surface? It's as if the whole surface out, the entire length of the fin from the base to the tip is all at the base temperature. That's what it is, right? And so it would be where this maximum would be the convection coefficient, my area, times theta base, or the temperature at the base minus the temperature of the fluid, the gas temperature. The temperature at the base is my temperature at I2, at Di2. It's this temperature right here, isn't it? Okay. What is my area? It's not my conduction area. It's my, isn't this area the perimeter times length? Isn't that P times L, perimeter times length? Okay, so for each of these, and I have 8 of them, then I know what is the Q through the 8 struts going out. So how do I get this efficiency? From a fin analysis with a fin parameter M. And then I know the length. Hey, what is my length for this problem? It's the L is equal to D naught minus Di2, but I have to divide that by 2, don't I? Because they're diameters, not radius. So my perimeter equation would be 2 thicknesses plus 2 lengths going deep. But one of those are negligible. Can I neglect the 2 thicknesses compared to the 2 lengths? Or can I neglect the 2 lengths compared to the 2 thicknesses? Which one? Its thickness is like 3 millimeter. And maybe I'm going to consider a 1 millimeter depth. Which one's negligible? This one's negligible. Fin parameter M, that's the square root of HP divided by KA. So C, I like to put a subscript C. That's my conduction area going out. We just said that the perimeter is 2L. The conduction area for a fin going out is going to be thickness times L. So when I do the fin parameter, you get the square root of H times 2 divided by thermal conductivity of the fin times the thickness. You could probably find that equation somewhere in our textbook, right? It's in chapter 11. Okay, so you use this. That's how you calculate the fin parameter. That's how you calculate the efficiency of the fin. Now, when I did the calculations for this problem, I calculated a fin, M being 36.5 something additional digits in their inverse meter. Oh, you already solved this problem. Wow, you're fast. And then I multiplied by L. The L is, what is it? I forget my numbers. I have them on the previous slide. But it's like 22.5 millimeter is L for my numbers. And then I get a fin efficiency of 0.82. I'm going to write it right up here. 0.8227, 82%, close to 1. All right. So it's like I calculated this, the H was given, the perimeter times the length. Again, we look at the perimeter. Hold it. This is area convection. I need to go slow here. The area convection would be this L here, which is the length of the fin multiplied by the length going down, and then you have two sides. So you have two, because I used L up here, right? What is that L? That L is the direction down the length of the, so we have like L for the length of the fin, and then L for the length of the tube in the direction, going in the direction of flow. A little confusing, sorry about that. So we're going to have 2 times the length of the fin. Maybe I should do that. Put the length of the fin. Length of the fin. Okay. 2 times length of the fin times the length in the direction of flow. All right. Professor, I'm really getting confused. Hopefully you're not getting confused. I want to have a resistance, TB minus T infinity, where this TB is T I2. Well, it's like 1 over the 8 eta convection coefficient 2 length fin L. That would be this resistance right here. Now, what I encourage you to do is go ahead and calculate a value of this resistance, a value of that resistance, this resistance, this resistance. Actually, what would be the units on each of these resistances? Isn't it degrees C per watt? And then, what should you do to these two resistors? Combine them because they're in parallel. And then what do you do with this one, and that combined? You add them in series. So go slow. I think you'll work it out. Now, if you come back and you want to change the assumption, and you want to have basically that this surface is not the same temperature as that surface, then you have a pathway and another pathway. So what you would do is you would modify this to have a network that went like this. Go from here to here to here to there. And so this would be the temperature at I2 under the fin, and this would be the temperature I2 exposed, no fin, if you think they're significantly different. And then this would be conduction just through this, and then you have the convection on the exposed, and then you'd have conduction through here, and then you have out through the fin. Don't do it that way. Do it the way I showed you, okay? Because I think if you do it the way that I've outlined here, you'll get within the 2%, and you'll get it graded correctly. Who already input? Did you already input your value in Wiley Plus? Did you get the 2%? First try? A+. Who else? I know, you're just going to give me whatever answer comes to your mind. You didn't do it. Who already did it in Wiley Plus? Did you already get it within the 2? Okay, you're still working on it. But it's easy to get outside the 2% and then scratch your head. So follow this approach. All right. We have saturated water vapor leaves a steam turbine at a flow rate of 1.7 kilograms per second and at a pressure of 0.51 bar. A little bit about this pressure. Is that a vacuum? 0.51 bar? It is. So, yes, you can have steam within pipes, but if you pop the hole in the pipe, air would rush in and not steam rush out because it's in a state of vacuum in that pipe. At 0.51 bar, it's in a state of vacuum. Okay. The vapor is to be completely condensed to saturated liquid. So it comes in saturated vapor, and you need it to come out saturated liquid. You're going to use a shell and tube heat exchanger that uses some city water. So as a cool fluid, the water enters the thin-walled tubes at 17 C and leaves at 57. Assume an overall heat transfer coefficient of 2000, so they give you U, and determine the required heat exchanger area needed. So there's the answer, but how are you going to calculate A? Well, this is where you would have the number transfer units. You need to get that, and you're going to basically get effectiveness, and then you calculate the NTU for that configuration. What do we have? Shell and tube heat exchanger. All right. So make a summary of information that you have, like the mass flow rate of the hot is 1.7 kilogram per second. What is the specific heat of the hot fluid? It's changing phase. It's going from saturated vapor to saturated liquid. It's undefined, but you would put infinity in their calculations. The cold fluid is the minimum heat capacity rate. Okay. Maybe I put over here the mass flow rate of the cold fluid. Do they give us the mass flow rate of cold? No, that's the second part of the problem. We don't know that one. And the specific heat of the cold fluid, well, you could look it up for water. It's around 2,000 or 4,200 for 4,178 joules, or 4.178 kilojoules per kilogram Kelvin. Specific heat of the cold fluid. Okay. So, okay, so if this of the hot is off to infinity, C of the cold is some value, what is CR? Well, it's the minimum divided by the maximum. Now, I didn't say the minimum goes to 0. It's some constant. But what does the maximum do? So what does CR do? 0. You have to make that observation, right? Okay. Okay. What is our effectiveness? Can we calculate our effectiveness? Well, it would be Q divided by Q max. All right. We have our mass flow rate, and we know it's going from saturated vapor to saturated liquid. Can you calculate Q? So what is the Q? The mass flow rate of the hot steam times HFG at 0.51 bar. And so the HFG, let me get the mass flow rate, 1.7 kilograms per second. The HFG is 2304 kilojoules per kilogram. So we calculate the rate of heat transfer, 3917 kilowatts. Where did we get that again? Only from looking at the hot fluid. So we know what we need to achieve. We're sizing our heat exchanger. Is Q that comes out of the hot equal to Q that goes into the cold? Yes. We just calculated what comes out of the hot is 3917 kilowatts. What goes into the cold from an energy balance of the cold? It's equal to the mass flow rate of the cold, the specific heat of the cold, and then the temperature change of the cold. It comes out at 57, or let me leave it in symbols. Temperature cold out minus temperature cold in. This one is 57, this one's 17, this one's 4.178. The only unknown is the mass flow rate of the cold fluid. Where did that equation come from? Well, energy balance. What's coming out of the hot goes into the cold. We calculate the mass flow rate of the cold fluid. and that's equal to 23.44 kilograms per second. Actually, that's the answer to part B before we get to part A. Well, why did I want that? Because I can now calculate the heat capacity rate of the cold fluid. It is 97.94 kilowatts per Kelvin. So that I can calculate Q max, which is the minimum heat capacity rate. We just calculated it, times the temperature hot in minus temperature cold in. So it's 97.94 temperature hot in. I need to get the saturation temperature at that pressure of 0.51 bar. Okay, let me pause right here. Can you find the saturation temperature 0.51 bar? Do you want to do that as a numeric input clicker or not? Or just call it out? Can you find it? You want a clicker? Do I have time for the clicker? Or we do? There you go. Put it in. What is that? In degrees C. We want it in degrees C. The saturation temperature of water at 0.51 bar. All right, so it comes in at a temperature of 82-ish. Let's stop. Grade this. 82. 81. We'll take it, we'll take it, we'll take it. Okay, 111, little off, 151, little off. So it's 81.8. I think that's out of a thermo book or some software I used. 81.8 or 82. Minus the temperature, the cold in is 17. So you get Q max. So once we have the maximum, which is 6,345 kilowatts, you could calculate the effectiveness. You calculate the effectiveness and it comes in 0.6174. How does that help me get the area? Well, you have to go to the correlation for the shell and tube heat exchanger. Okay, shell and tube right here. All right. So we come back here. And what did we have for our effectiveness? 0.6174. Well, this is 0.6174 right there. Look good? What was our ratio C min over C max for this problem? One fluid was changing phase? 0. 0. So 0.61, come over here. So I read off, number of transfer units is about 1 for a shell and tube heat exchanger. If I'm really good, I'll read it off to be 0.9607. Where'd you get that from? The equation instead of the plot. The plot would say I'm at 1. Let me see if, well, they show you the equation right here. They're saying the equation 1130. 11.30. Okay. I don't know if I have the equation 1130 anywhere here. So here it is. If you want to do it to code it up, you would first calculate this parameter E. So 2 over the effectiveness. And then you have the C sub R we calculated. It's a little bit of work. I think this E comes in at 2.23955 for my numbers. And then you put in the E here with the C sub R and you calculate the number of transfer units for one shell pass. That's all we have. And that gives us the 0.9607. 0.9607. Okay, so now let's get back to our problem. How do I, now that I know the number of transfer units is 0.9607, how do I use that to get the area? Well, that's defined as UA divided by C min. So the area is the number of transfer units times C min divided by cap U. There's cap U. C min, we calculated right here. We just calculated number of transfer units. You just solve for area, and there it is, 47 meters squared. The problem continues because after a long time, extended operation, the fouling causes the overall heat transfer coefficient to decrease. It goes from 2,000 to 1,000 watts per meter squared Kelvin. To completely condense the vapor, there must be an attendant reduction in the vapor flow rate. So they're going to reduce m dot of the hot fluid. It's going to go down, reduction, for the same water inlet temperature and same water flow rate. Now, did that say the same water outlet temperature? No, just the same inlet temperature of the water and the same water flow rate. What's the new vapor flow rate required for complete condensation? Well, okay, let's ask this question. C min, is that still linked to the cold fluid? And did that change? If I didn't change the mass flow rate of the cold fluid, did it change? It didn't change. No change. Okay. How about the number of transfer units? Well, that's UA divided by C min. Did the area change? No change in the area. Did the minimum heat capacity rate change? No, the flow rate of the liquid water didn't change. What about U? My U changed. It went from 2 to 1. So what happened? You think about the number of transfer units now is half of what it was before. So the number of transfer units is half of 0.9607. So the number of transfer units is now 0.48034, something like that. You can go back to the plot that we just showed, where you just, instead of the NTU being 1, you move it over here to 0.48. You come up to the same line, C sub R 0, and you read off the new effectiveness. Then with the new effectiveness, you can multiply by the Qmax to get the actual rate of heat transfer. The actual rate of heat transfer is the mass flow rate of the hot fluid times HFG. It's still saturated vapor to saturated liquid. And this has to go down. You get a new mass flow rate, which is now 1.05 kilograms per second. So instead of 1.7, you only can condense 1.05 kilograms per second. You don't need to use the plot. You can use the equations, do the same thing. But you'll look for the equation where you're given the NTU and you need the effectiveness for 1 shell pass. So I have a cross-flow heat exchanger. It's used to cool air using water. This is like a chilled coil that we just talked about. Air conditioning in this building. You have airflow coming over. It's maybe 75 degrees F, and you want it to come out 55 degrees F, and then that cold air is dumped into the building in this room and other rooms. They're using water, okay? So it's to cool the air using cold water. The water flows in the inside of tubes and the air on the outside. That's often true. Fins are used on the air side to promote heat transfer. Why? Because air is notoriously a poor, convector. So it has a low thermal conductivity, hence you fin that side. The overall thermal resistance is dominated by the air. So the 1 over U A is my overall thermal resistance. And you have the 1 over the HA on the air side. You have any conduction, L over KA, through the material separating the two. And then you have the 1 over HA on the water side. Basically negligible, negligible. This is what dominates their thermal resistance. How will the overall heat transfer coefficient, that's cap U, change if the mass flow rate of air goes up? Will U increase, barely change, or will U go down? You done? Okay, let's stop it and we'll take a look at the results. And the results are kind of all around the place. Well, from our understanding of external convection, if you have a greater velocity, maybe it becomes turbulent, maybe it was already turbulent, but it's even stronger with the higher Reynolds number, you're going to increase and promote convection heat transfer. I mean, think about the little kid, right? I don't know if you ever grew up, and I have grandchildren now, and so that you serve them some food, right? And they're about ready to throw that spoonful of something into their mouth, and what do you say? Foof it, foof it. Don't burn your mouth. They can't see how hot it is. They get it in their lips or tongue, and then they cry, right? So you're always like, that's hot, that's hot. Okay, I know you have long time since you were a kid or been around children, but believe me, you sit down with some hot food on a table, the kids will throw it in their mouth and burn themselves, right? Foof it, foof it. Blow air on it to cool it. You're going to convection coefficient goes up. So anyway, U will also go up. The overall heat transfer. Basically, it's 1 to 1. If this dominates, okay, well, let's go through this one. If the mass flow rate of water is now increased, how does the overall heat transfer coefficient change? Will it increase? Will it barely change? Or will it decrease? We're done. Let's stop it. And we'll show the results. Well, it'll barely change. Why will it barely change? Because the water over here, yes, you're going to change that H. But it's not going to be that significant. Let's say a friend of yours has one of these huge pickup trucks, and they're going to go on a long road trip, and they want to increase the mileage, the MPG. So he gives you a screwdriver and says, remove my side mirrors. I want to improve my MPG. Well, would you remove the side mirrors, or you say, come on, that's going to be a negligible effect? It's a negligible effect. There's a lot of things in engineering like this. And believe me, when people are out there in practice, somebody will be like, okay, let's turn up the flow of water to improve it. And it's not going to have the big effect. All right. I'll be able to leave that alone. Thank you very much for your attention. I'll see you on Monday.